Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast, in which we look at lectures and homework problems for organic chemistry. In today's homework problem, you were asked to draw a labeled orbital diagram for the molecule CH3CHS. In some ways, this is a trick question because in order to draw a labeled orbital diagram, you have to determine the hybridization of each non-hydrogen atom. In order to do this, you have to come up with the hybrid orbital number, which means you need to know the total number of atoms bonded to each non-hydrogen atom and lone pairs. Since the lone pairs may not have been shown, you have to remember to draw the Lewis structure. To draw the Lewis structure, I've got to determine the total number of valence electrons. So the total number of valence electrons. Total number of valence electrons for this molecule. What do we get? Well, we have 2 carbons, so 2 times 4. We have 4 hydrogens, so plus 4 times 1. And then we have a sulfur, which has 6 electrons, so plus 6. Valence electrons. If I that's 8, 12, we get 18 electrons, or 18 valence electrons. So now I can begin setting this up. I have a carbon with 4 electrons. I have another carbon with 4 electrons. I have a sulfur with 6 electrons. 6. And then I can put my hydrogens around it. I have 3 hydrogens off the first carbon. And I have a hydrogen off of the second carbon. So if I start linking up the hydrogens off the first carbon, I see each hydrogen gets 2 electrons as it needs. Carbon has 2, 4, 6. Carbon has 7. Link it to the other carbon. This carbon now has 8. Link up the hydrogen to the carbon. I've got 2, 4. And I go 5, 6. And bring the other one. 5, 6, 7. And there you go. I've linked up all the electrons. Sulfur has 2, 4, 6, 7. I'm ready to draw my Lewis structure. So I can do this. And once I'm done drawing my Lewis structure, I should be able to figure out the hybrid orbital number. So it looks like there is a double bond to sulfur and 2 lone pairs. So now I can label these. I can label these carbon alpha, carbon beta. And I can calculate an HON, a hybrid orbital number. Hybrid orbital number for carbon alpha. If I do that, the hybrid orbital number for carbon alpha, we have the carbon is 3 hydrogens and 1 carbon attached to it. That's 4 atoms. No lone pairs, so 4 plus 0 equals 4. If I take the hybrid orbital number for carbon beta has how many atoms attached to it? Notice we're not counting bonds, we're counting atoms. Well, the carbon is attached to a sulfur, a hydrogen, and carbon. That's 3 atoms. Are there any lone pairs? No lone pairs. So its hybrid orbital number is 3. And the hybrid orbital number for sulfur? For my sulfur equals, Well, sulfur has only one atom attached to it, but it has two lone pairs, so it has a hybrid orbital number also of 3. Now remember, hybrid orbital number of 4 is sp cubed. Hybrid orbital number of 3 is sp squared. So these are the hybridizations of those atoms. And we can label them sp cubed, sp squared, and sp squared. So, we're ready to proceed now, begin with the construction of our hybrid orbitals and making our labeled orbital diagram. I'm going to redraw what we've determined now. So here's the molecular formula again, but this time I'll show the lone pairs. Two lone pairs here. And this carbon was sp cubed. This guy's sp squared. And this sulfur's sp squared. Okay, so we're ready to begin drawing this, and I can start with the sulfur if you like. So I'm going to make it fairly large. Here's my sulfur. And I'm going to make an orbital in this direction. And I'm going, since it's sp squared, I draw the pattern that I had to memorize and learn for sp squared. And that's linked to a carbon who is also sp squared. Oh, let's make him as big as the sulfur. Okay? And so he'll have his orbitals here and here. Now, off of that carbon is another carbon. You notice I haven't put in the 2 p's yet. I will come back and do that. I'll just finish drawing my carbons. And he's sp cubed, so I have to remember the shape for sp cubed. What were the shapes? The shape for sp squared was trigonal planar. So I drew my sp squared in a tilted trigonal planar. And the shape for sp cubed is tetrahedral. So now I can put the h's in. There's the H here. So we're ready to draw the 2 p's, and I didn't draw them first because I want to use a different color. So I'll make a large 2p. There's one lobe of it. So this full figure 8, or this dumbbell shaped, is a single 2p orbital. And the sulfur, because it's sp squared, has a single 2p orbital. Okay, now we can put in our electrons, and I'll use black for the electrons. And I can start with the carbon. I'll start with the sp squared carbon. Carbon has 4 valence electrons, so I draw the 4 valence electrons. And I draw them all pointing up. Now, notice every lobe doesn't get an electron. If I did that, I'd put 5 electrons. That'd be too many. I can't put 2 electrons in this because this is a single orbital. And for carbon, all its single orbitals had 1 electron. So only one goes in the sp squared, one in the 2p, one in the sp squared, and another one in the sp squared. And there's my 4 electrons. The other carbon has 4 electrons, 1 in each orbital, but I have to make them opposite spin because according to the Pauli exclusion principle, only 2 electrons in an orbital and they must be opposite spin. So I make all those carbons arrows for electrons pointing down. This lets me put in my hydrogens that are off those carbons, and I can do that. Be careful not to miss a hydrogen atom. This hydrogen's very easy to miss. And make sure you have, in a single orbital, opposite spins. So now we're ready for the sulfur. The sulfur had 6 valence electrons. 1 goes in this to make the bond, sigma bond to carbon. 1 goes in the 2p because you got to remember when you link this up with the other 2p, okay, so when these link up, you've got, this becomes a single orbital that can hold 2 electrons. So you've got 1 electron here and the other electron of opposite spin. So that's why you show a linkage here. Now, so that means I put 2 electrons of sulfur. Sulfur is 6. So These guys out here are the lone pairs, so I can put 2 down and then finish off the lone pairs, and those are the 6 electrons. Now in the labeled orbital diagram, you're often requested to show the hybridization. Well, we've done that by writing under the labeled orbital diagram, and in the previous slide, if we asked to show our work, in the previous screen that I had erased, I had shown my work for getting this. And then I'm asked to draw the labeled orbital diagram, so I drew the proper hybridization shapes, and you're often asked to put in electrons. Now, here's the question. Some other things you're often asked for is to label the bonds and show bond angles. Let's start with bond angles. Okay, SP squared, remember in this course we're utilizing a bond angle of 120 degrees because it's trigonoplanar. So what kind of bond angle do I put here? That bond angle right here is 120 degrees. Or is it? If you did this and marked it as 120 degrees, you are wrong. Why? Can you spot why? This is not a bond angle and would not be labeled in an answer to a test. Not a bond angle. Why? Well, it's not a bond angle because bond angles are angles measured from one bond to another bond, from here to here. And that one is 120 degrees. What are we measuring the angle of here? The angle here is an angle from a bond to a lone pair. And a lone pair is a non-bond, a non-bonding pair of electrons. So that is an angle you would not measure. So I'm going to take it out. I'll have to repair my 2p orbital. Okay. So I took that bond away. So we'll erase that. And you wouldn't label that. When you're showing your bond angles, you would not label it. Also, once you've labeled one angle around the atom, the other angles are the same. So you can just label one of the angles. When we measure the angle here, or here, or here, or here, it's all the same. So I'm going to measure this angle. And I'll put that here. What's the angle in SP cubed? The angle is 109.5 degrees. So I've labeled my bond angles. All that remains is to label my bonds. So let's start with my bonds. What is this bond? Well, it's a head-on collision between hydrogen, which uses a 1s, and what was the hybridization of this carbon? This carbon was sp cubed. So it's a head-on collision, that's sigma, and we say 1s, comma, sp cubed. Now you could say sigma 1s sp, sigma sp cubed 1s. The order here doesn't matter. Okay, what about this bond? Well, it's a head-on collision between hydrogen, and this time the carbon's using an sp squared. So this is a sigma 1s sp squared. Okay, so we have a sigma 1s sp squared and several sigma 1s sp cubes. Now, if you just label the one, I will assume you're saying the other hydrogens on the same carbon are also the same. So if there's something different going on, make sure you label it. Okay, what about this bond? Well, we have a carbon that's sp cubed bonding to a carbon that is sp squared. And so since sp cubed and sp squared collide head on, we have a sigma sp cubed sp squared. So we have a sigma sp cubed sp squared. And I'm, just so you can see the bonds, I'm going to, well, I'll underline them later. What about the carbon-sulfur sigma bond? The blue one here. Well, this blue one is also a sigma bond. Sulfur's sp squared, carbon's sp squared, so it is a sigma sp squared. sp squared. And again, the order you write these labels down is not crucial. And lastly, we've got our red bond, so I'll change to red. Our red bonds caused by overlapping. What are those orbitals? 2p's. 2p's, aren't they? So we have a pi 2p orbital. Now, if you wrote pi 2p, you have made an error. It's not 2p, is it? Take a close look at sulfur. Look sulfur up on the periodic table. Pause this video and grab a periodic table in your textbook somewhere and look it up. Sulfur is below oxygen in the periodic table. Sulfur is in the third row. Its valence electrons are using 3s and 3p. So this is not a 2p orbital. This is actually a 3p. Carbon is using a 2p. So this is wrong. I should have written a pi 2p 3p. And that was one of the tricks. Notice we don't label. We can label them, but they're not bonds, so I wouldn't label them. But these are non-bonding electrons, so we weren't asked to label them. So let's just underline in, oh, what color? Let's try green so it'll stand out. So we've got a bond here, bond label here, bond label here. We've got one here and one here. Okay? So you see all the bonds are labeled. And what we've done here is we've determined the Lewis structure to get the lone pairs, found the hybridizations, drawn our patterns that we've studied for, built up our structure. And once we've done that, we've put in the electrons, joined the pi bonds together, labeled bond angles, and labeled all the bonds. Well, there you have it. The labeled orbital diagram for CH3CH. Thank you very much.